Number 25. If 3x to the cubed y to the fourth equals 24, then dy dx at the point 21 is equal to what? Well, I see some implicit differentiation here because we do have an x and a y both on the same side of the problem. So just remember on these ones, whenever I take the derivative of y, we will attach dy dx. All right, I do notice on the left side also we have a product, so I'm going to be using the product rule. So if f is 3x to the third, f prime will equal 9x squared. And then if g is y to the fourth, g prime will be 4y cubed dy dx. Don't forget that part of it. Okay, then from here we're just going to go ahead and take the derivative using the product rule. It will be f prime times g. I'm just going to write that down. F prime times g plus f times g prime. So f prime is 9x squared times g, and g was y to the 4, plus f times g prime, 4y to the third dy dx, and then equals the derivative of 24 is just 0. Okay, I'm going to clean this up before I try to solve. I'm going to have 9x squared y to the fourth plus, I can multiply the 3 and the 4 together, and that will give me 12 x to the third y to the third dy dx equals 0. Okay, anything that doesn't have a dy dx in it, we're going to relocate on the right side of our problem, so we'll have to subtract it from the left side. So now I'm going to get 12x cubed y cubed dy dx equals negative 9x squared y to the 4. And then we'll divide both sides by 12x cubed y cubed. And so now I'll have dy dx equals, you could easily keep it how it is, but I'm going to simplify it a little bit just because it's going to be easier to plug things in. So negative 9/12 will reduce to negative 3/4. And then x squared over x cubed will reduce to x in the denominator. Y to the fourth over y to the third will reduce to y in the numerator. So that's my derivative, and it asked me to evaluate it at the point 2, 1. So now all I need to do is plug in 1 for the y and 2 for the x, and when I do that I get negative 3/8. Okay, number 26, find dy dx if 5 cotangent y minus 4y squared equals 8x to the 4. Again, we're going to have some implicit differentiation because we have both x's and y's in this problem. Okay, the derivative, 5 tags along because it's a constant. The derivative of cotangent is negative cosecant squared. So this will be negative 5 cosecant squared y, and then don't forget the dy dx, minus the derivative of 4y squared would be 8y, and once again dy dx, and then equals the derivative of 8x to the 4 would be 32x cubed. Right, from here, let's factor out a dy dx from that left side. When I do that, I'll get negative 5 cosecant squared y minus 8y equals 32x cubed. And then to get dy dx by itself, we'll just divide by that quantity on the left side. So we'll get 32x cubed over negative 5 cosecant squared y minus 8y. And then that would be my derivative. Okay, number 27, a nice related rates problem for us. Air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20. And they did give us the hint, the volume of a sphere is volume equals 4/3 pi r cubed. So remember, the first thing that we want to do is write down the information that they give us. They did tell us that air is being pumped in at a rate of 5 centimeters cubed per minute, so that's how fast the volume is changing. So dv dt will equal 5, and it will be positive because we're putting air into the balloon, so that's getting bigger. And then determine the rate at which the radius is increasing. So they're asking for how fast is the radius changing, so we want dr dt. And then they did tell us that the diameter is 20. Since there's no diameter in these problems, we're going to go for radius. So if they tell us that the diameter is 20, the radius would be 10. Okay, so now from here, we got our information down. The next thing is we want a formula, which they very nicely gave us. And then the next step is actually to take the derivative. So the derivative of v would be dv dt. And then on the right side, bump the 3 out front. I'll get 4 pi r squared. And then don't forget, we also have to include the dr dt. Now from here, we're just going to plug in information. dv dt was 5. Then I have 4 pi. R was 10. And then we're solving for dr dt. So this will be 5 equals 400 pi dr dt. We'll divide both sides by 400 pi. And you may leave it as 5 over 400 pi, or you can divide this out, just make sure that the whole 400 pi is in parentheses if you decide to do that. So dr dt equals 5 over 400 pi, the pi is on the bottom, or that is equivalent to 0.004, and if we do need units in radius, my radius would be measured in centimeters per minute. So that would be my answer for that one. Okay, for 28 and 29, let f be a function defined on the closed interval 0 to 3.5. The graph of f prime is shown below. 28, find the x-coordinate of each relative minimum of the graph of f on the closed interval from 0 to 3.5 and justify your answer. So if we want to find minimums, we're looking for f prime. So we're going to make an f prime chart. Since this is a picture of f prime, we will be looking above and below. So if I'm looking at this, I notice I change from being above and below at 1.5 and again at 2.5. Okay, my picture is above the x-axis till I get to 1.5. It's below the x-axis until 2.5, and it is above after that. So if I would like to find a minimum, I know minimums occur where f prime changes from negative to positive. So when it says the x-coordinate of each relative minimum, that would be occurring at x equals 2.5. And justifying my answer would be because at that spot, f prime changes from negative to positive. Okay, for number 29, on what intervals, if any, is the graph of f concave down? Justify your answer. Okay, concavity has to do with the second derivative, so we want to do f double prime. If I'm at f prime and I'd like an f double prime chart, we're going to be looking at the slopes. Okay, so if I'm looking at the slopes, my slopes are going up, or they're going to be positive till I get to 0.5. And then they are negative all the way till I get, we'll say 2 is our turning point. It looks like a little bit before that, but we'll just kind of go with that. And then they're going up again till I get to 3, so their slopes are positive till I get to 3, and the slopes then are negative again after 3. So when it said on what intervals is the graph concave down, it would be these two areas right here. So we could say that would be from 0.5 to 2, and then 3. It won't be till infinity because this graph ends at 3.5. So from 3 to 3.5, and then we do need to justify. That would be because f double prime is negative. And there we have it.